So our next topic is anaerobic digestion. Okay. So so far I think we talked a lot about like aerobic processes, bioprocesses. We talked about activated sludge process and some other processes, and then this morning we also talked about composting. So the next one is anaerobic digestion process. So anaerobic digestion process, I think already some of you are familiar with the process. It's a multi-step biochemical process where actually microbes, anaerobic microbes, so those microbes for their metabolism, they do not need any oxygen. Okay. So in absence of oxygen, they break down the organic compounds that you have in your organic waste, and they can produce methane. Okay. So carbon in organic waste is reduced to methane, and there are two types of microbes work together. So two types of anaerobic microbes, we call them bacteria. I think most of you are familiar, but another type of microbes also actually work in anaerobic digestion process. We call them archaea. So bacteria is basically they break down the organics, okay, and actually produce some simple compounds and hydrogen gas, and then in the final step archaea further convert them into methane gas. So not necessarily.
Archaea is umbrella name for methanogens.
Yeah. So for methanogen we call them archaea, not bacteria. Still, if you see some old books, maybe that is actually published in 1990s or before that, or even early 2000, you are gonna see they call it methanogenic bacteria. Even still, I can see sometimes I get to review paper, okay, and I see people use methanogenic bacteria, which is not correct now. Okay. So previously they used to be actually bacteria and archaea, they have lot of similarities. Okay. They look almost the same size and shape. They also actually kind of grow by binary fission like bacteria.
Even the identification process is
similar. But the major difference in their cell wall. So for bacteria they have peptidoglycan, archaea they actually the cell wall is more on lipid. Okay. So they don't have peptidoglycan like bacteria, and some archaea they can actually grow in some extreme environment where actually bacteria cannot grow, like about 90 or even close to 100 degrees Celsius. Some archaea have been found they can grow. Okay. So let's come back to the anaerobic digestion. So in addition to organic waste like food waste or yard waste, we can actually use a wide variety of feedstock for anaerobic digestion process. So for example, we can use agricultural biomass, we can use manure, we can use sludge that is actually produced from wastewater treatment process. Anaerobic digestion process can also be used for wastewater treatment, but that wastewater needs to be actually high strength. Okay. So not like diluted wastewater we have in like domestic wastewater. Like if you remember from our previous lecture, COD. So what is the COD for domestic wastewater? What is the range? You remember? 400 to 500, right? But for anaerobic digestion process you need at least few thousand milligram per liter of COD. Okay. So you can still use it for wastewater. So for example, like some countries like some European countries, they have source separation of wastewater. So for example, the wastewater that is coming from toilet, that is actually kind of considered as black water, and that is actually treated in anaerobic process. But wastewater that is coming from other places in your home, for example from your kitchen sink, laundry, from your shower, typically you don't have high organic content, right? So sometimes they actually recycle that waste. So they use some physicochemical process and recycle that gray water for, let's say, gardening or some other stuff. Okay. So you can still use anaerobic treatment for wastewater, but it has to be concentrated. So anaerobic digestion process can give us biogas, which is mainly rich in methane. We can actually like combust them in combine heat and power generation unit and produce heat and electricity. Another option is we can upgrade the biogas to renewable natural gas by removing carbon dioxide and some other impurities like sulfide, and you can actually use is as an alternative to natural gas. Okay. Another evaluated resource that we can get is the digestate. So anaerobic digestion process can remove organics, mostly organics, but at the end of the process some organics still remain, okay, in the digestate, and lot of nutrients like nitrogen and phosphorus gonna be in the digestate. So that is actually a good biofertilizer for plants, but again you cannot directly apply them to the land, you have to meet certain criteria. Okay, different countries follows different criteria, but more or less most of the countries they adopted those criteria from US EPA, US Environmental Protection Agency. So if you have pathogen content under a certain limit, we call them class A, and we can actually use it anywhere. But if pathogen content is high, that is considered as class B, you have some limited application, you cannot actually apply it anywhere. So process fundamentals, it's a multi-step biochemical process. So that means there are multiple steps involved in the process, okay, and multiple types of microorganisms, they kind of work together, okay. So we call it synergy. So one metabolite produced by some microbes is utilized by another type of microbes, okay. So it's a very good synergy among different types of microbes, or syntrophic interaction, okay. So the process involved more or less like 4 steps: hydrolysis, acetogenesis, and then final step is methanogenesis. Some books you are gonna see they consider hydrolysis and they combine acetogenesis and acetogenesis together and call it fermentation, okay, and then the final step is methanogenesis. But again it's like if it comprehensive if you divide the different biochemical steps, you have 4 steps involved. So first the process start with hydrolysis, where actually complex organics like carbohydrate, lipid, protein. So if you consider any kind of organic like food waste, you mostly have carbohydrate, proteins and lipids, right? 3 types of organics. So in first step, some microbes they actually have enzymatic activity, they break down those complex organics to simple organics, low molecular weight simple organics. For example, carbohydrate can be hydrolyzed to sugar, protein can be hydrolyzed to amino acid, and fat can be hydrolyzed to fatty acid, okay. So then actually other fermentative bacteria, okay, so they do 2 type of process, acidogenesis and acetogenesis. They use those soluble organic molecule and then they produce something called more simple organic volatile fatty acid like propionate, acetate, butyrate, okay. So and then some other microbes further break down those volatile fatty acid to acetic acid. Acetic acid is actually also a type of volatile fatty acid, okay. So but let's say if you have in this process, if you have butyric acid or propionic acid, they are actually further break down into acetic acid, and the process also generate hydrogen and carbon dioxide, okay. So acetic acid, hydrogen and carbon dioxide, those 3 are the major precursor for methane production, okay. Then you have the final step where methanogenic archaea, they are not bacteria, they are archaea. So there are mainly 2 types of archaea. So one type of archaea, they use acetic acid and then convert acetic acid into methane plus carbon dioxide. So we call them acetoclastic methanogen, okay. Acetoclastic methanogen actually use acetate and produce methane and carbon dioxide. On the other hand, another type of archaea, we call them hydrogen trophic methanogen, okay, or hydrogen utilizing methanogen. What they do, they use hydrogen and carbon dioxide and combine them and produce methane. So that step doesn't produce any carbon dioxide, but this step actually produce some carbon dioxide, okay. And and most of the time anaerobic digestion process you have 40 to 70% methane and 30 to 50% carbon dioxide. So still a significant portion of carbon dioxide, and most of the time like it has been found that actually acetoclastic methanogen, they are much more dominant in most of the digester. Okay, but it has been found that actually hydrogen trophic methanogen, they are more resilient. Okay, if you have some unfavorable metabolic condition, they can survive better than acetoclastic methanogen. So like composting process, there are some optimum process parameter for anaerobic digestion process as well. So for example, they prefer neutral pH 6.8 to 7.2. You need to provide enough alkalinity. Okay, you must have enough buffer in the system. Why? Because if we go back, the process actually produce volatile fatty acid or organic acid, right? So when you have organic acid, it is going to actually consume some of the buffer to neutralize, right? So you have to make sure that you have enough buffer in the system, otherwise pH gonna drop. And once pH drop, it doesn't matter, you adjust the pH back to neutral pH, it's not gonna work. Okay, it's kind of like some sort of irreversible process. So if acidification happen in your digester is gone, you have to restart. Okay, and alkalinity you need from 2000 to 5000 milligram per liter as calcium carbonate, and carbon to nitrogen ratio optimum is between 20 to 30, close to and here we can do the same thing. This morning we learned the concept how to actually estimate, okay, different types of feedstock can be mixed together to achieve some desired carbon to nitrogen ratio. So we can apply the same concept here, okay, as I mentioned. So those microbes also need nutrients. Under macronutrients they need nitrogen and phosphorus. Under micronutrients they need different types of metal like iron, because iron is needed to actually boost the enzymatic activity of microbes, copper, zinc, nickel, but we don't need to add them. Typically we consider that in incoming waste or wastewater, whatever dissolved metal you have, possibly it's enough, or dissolved micronutrients you have, maybe it's enough for the microbes to grow. Toxicity, it's a major problem. So when you operate the anaerobic digestion process at higher organic loading rate, okay, then you could have different kind of problem. What different kind of problem? Let's go back here. So typically bacterial process, so the steps done by bacteria, they are faster process, okay, but archaea typically they are slow growing microbes. Okay, so that means your process for bacteria, it's going to, so their growth kinetics is faster than methanogen. So now you are running your reactor at high organic loading rate. Now bacteria, they are working very well, they are producing volatile fatty acid, okay, at very high rate, but your archaea, they are slow growing microbes, so they cannot cope up with the metabolism or rate growth kinetics of bacteria, right? So at some point what's going to happen, you are going to have volatile fatty acid accumulation in the system, right? They are producing at a higher rate, but methanogen, they cannot consume them at a higher rate, right? So some organic acid may be actually accumulate in the system, so now they are going to be acidification. So that's why process disturbance, it's a very common problem in anaerobic digestion, especially when you operate at higher organic loading rate. Like yesterday we learned about BOD loading, right? So V S naught divided by V of the reactor, right? So sorry, Q S naught divided by V. So the same thing actually works for you. Have a, when you operate the digester at higher organic loading rate, you have more disturbance in the process. And sometimes process can also be inhibited by ammonia, process can be inhibited by sulfide, okay. So especially for ammonia, let's say you have food waste, sometimes you can have very high protein content, right? So protein, when it's hydrolyzed, it releases significant amount of ammonia, and at high pH and temperature, ammonia can be mostly in the form of free ammonia gas, and free ammonia gas can actually kill the microbes, okay. So you can have different types of toxicity by organic acid, ammonia, sulfide, and mixing sometimes actually it's so mixing, it's kind of like a very I would say it's a puzzle for researchers still. So we kind of believe that okay, high mixing means we have no mass transfer limitation, right? So process can be actually like you can very high mass transfer rate and process can work better, but that's not necessarily the case. Okay, so higher mixing can actually negatively affect sometimes the microbes. Actually, we also did a study. It was done actually with one visiting student from IIT Kharagpur. Actually, he worked with me for a year before COVID, and we did some study on mixing, and we found that actually like high mixing, so it's kind of like it can impact the microbial community. So you need some sort of moderate mixing or intermittent mixing. Maybe you mix it for like 15 or 20 minutes, okay, and then you leave it for 1 hour without any mixing. Then you mix it again. So not necessarily high mixing can give you better performance. So sometimes for digestion process, you also need to optimize the mixing intensity. Based on temperature, typically we have two types of anaerobic digestion process, mesophilic or thermophilic. So there is psychrophilic as well, but psychrophilic is not very common. Most of the time mesophilic at 37 degrees Celsius, it's a common industry practice, 35 or 37 degrees Celsius. So you can see here at different temperature, growth rate of anaerobic microbes is different, right? So at psychrophilic temperature, growth rate is low, mesophilic is moderate, thermophilic is kind of good. But why thermophilic is not a common practice? Any thought?
Maintaining temperature requires induction.
Huh?
Maintaining temperature is expensive.
Yes, that's one thing. Other reason? Sorry? Sorry, I could not understand. Okay, actually well, not necessarily there is inhibition. Okay, so what if I'm understanding you correctly, you are trying to say at high temperature it can be inhibited, but actually not, because it's growth rate. But yes, at some point it can be inhibited. And when? Because faster at high temperature means faster rate, and at high temperature when you have faster rate, you can have more imbalance between bacteria and archaea. Okay, so you can easily see like at high temperature bacteria, they are producing lot of volatile fatty acid, but methanogens still they cannot actually cope up with them. Okay, so you have more acidification problem or process disturbance at thermophilic temperature. Okay, so that's why mesophilic temperature is the most common practice. But yes, high energy input is one thing. Like obviously compared to 37 degrees Celsius or 35 degrees Celsius, at when you run your digester at 57 degrees Celsius, it is going to cost you more. Okay.
So mesophiles are responsible for production of reagent.
Sorry, mesophiles. Well, both can actually produce, but the problem is so let's say
So to answer your question, what I am feeling that why we are not going for higher temperature, because mesophiles and thermophiles need to stay together.
well, when you run at thermophilic temperature, everything gonna be thermophile. At that time, actually, like let's say you start a digestion process using mesophilic inoculum, and you are running at thermophilic, then most of the time mesophilic they are going to actually disappear from your system. Mostly it's going to be thermophile. But the problem is not between mesophile or thermophile. The problem is about imbalance, and that imbalance is going to be even more intense at thermophilic temperature. Okay.
We can maintain the number of population of thermophiles at a temperature of mesophile. But if we opt for the thermophile, it's very hard to manage the mesophile population.
Yes, we found that actually mesophilic, it's kind of they are much more resilient. Okay, if you let's say collect your inoculum from a digester that is actually operated at 35, and if you run them at 25 or 30 degrees Celsius, still it works good. But if you try to do some experiment with mesophilic inoculum and try to do some thermophilic experiment, it never actually work properly. So thermophilic, they are much more sensitive. Okay, so they are much more sensitive than mesophilic. Their growth rate is high, their decay is also very high. Okay, so they can grow very fast, they can also die very fast. So that's why actually mesophilic, okay, most widely used. So now they are depending on your type of the feedstock that you use for your digester, okay, especially the solid content, okay, there could be two types of anaerobic digestion. So if you are dealing with some wastewater sludge or high strength wastewater, it's mostly homogeneous, right, mostly water and very less amount of suspended solid, maybe 5% or 2%, right. So when we have very low solid content, especially less than 15%, we call it wet type anaerobic digestion. So wet anaerobic digestion. But when we are dealing with high solid content feedstock, so for example like food waste, yard waste, okay, so typically they have moisture content, let's say 60 or 70% and 20 to 30% solid, then the process is called dry or high solid anaerobic digestion. So there are many terms used for high solid anaerobic digestion. Some people use dry anaerobic digestion, some people use high solid anaerobic digestion, some people use another term solid state anaerobic digestion, okay, but I am okay with other terms, but I don't like the term dry anaerobic digestion. Dry means microbes, they cannot survive under dry condition, right, they need moisture, so it's not dry. I am okay with using high solid or solid state, but typically I use, because in Canada industry they mostly use the term high solid anaerobic digestion or HSAD, okay. So in this lecture we are going to learn little bit more, focus on HSAD, because today we are kind of like, you know, I think last 2 days we got enough of wastewater, so we want to focus little bit more on solid waste side. So I am going to, rest of my lecture I am going to be mainly focusing on high solid anaerobic digestion. But before we jump into high solid anaerobic digestion, I want to talk little bit more what are the pros and cons of wet and high solid anaerobic digestion. By we can have a side by side comparison of both process. So you can see wet type anaerobic digestion, it's we need like, you know, low solid content feedstock like less than 15%, but we don't actually run it at 15%. It's mostly I would say 2 to 5% or can be 7%, okay, because
Percentage is by volume or by mass, sir?
it's a, sorry,
As total solid 15% you are saying,
it's solid content, total solid,
by volume or by mass?
it's by volume. So milligram per liter, something like that. So if you have, let's say 2%, that means it's going to be 20,000 milligram per liter. Okay. So if you running at 5% solid, that means 50,000 milligram per liter total solid.
So all of them then they will be like semi-solid material.
It's semi-solid, yes. Waste or wastewater, it's semi-solid, right? So you have both suspended solid, you both have soluble organics in there. But when you have high solid, we try to maintain solid content higher than 15%. It can be up to 30%. Some commercial process they claim that they can handle up to 40%, but more or less it's about around 25%. Okay, most of the facilities high solid anaerobic digestion they operate at 25%. And solid removal efficiency, wet type anaerobic digestion it's higher, 50 to 70%, but in high solid anaerobic digestion it's mostly less than 40%. And why is that? Because high solid anaerobic digestion they handle more heterogeneous feedstock, right? So that's why obviously the efficiency of solid removal going to be little bit less than wet type anaerobic digestion. wet type anaerobic digestion is operated in continuous or semi-continuous mode, but on the other hand high solid anaerobic digestion most of the time like it's actually operated in batch mode or fed batch mode. And wet type anaerobic digestion you can provide continuous mixing, but high solid anaerobic digestion you cannot mix actually, honestly speaking, completely. It's kind of very, there are some commercial design where you can provide mixing, but the common technique is actually you have a solid tank where you actually load all the solid material, okay, and then you have liquid inoculum and you recirculate between two tanks and provide some sort of like passive mixing in the process, okay, high solid anaerobic digestion. So not totally mixed, but you can provide leachate and biogas recirculation. And wet type anaerobic digestion you have less amount of solid content and very high amount of water, okay. So typically the footprint of wet type anaerobic digestion process is much bigger, so you actually have large system, and mostly because in your feedstock you mostly have water, right. But on the other hand the benefit of high solid anaerobic digestion is you are actually dealing with high solid content feedstock, so and less amount of water, so footprint is lower than wet type anaerobic digestion process. So obviously when footprint is low your heating cost also going to be low, right. So you have a, instead compared to large tank, if you have a smaller tank, smaller footprint, so smaller you know like a lower heating cost for digester heating. Wet type anaerobic digestion it can work for only specific feedstock, it can work for wastewater sludge, it can work for food waste, but food waste if you want to go for wet type anaerobic digestion process you have to do some you know pre-treatment like grinding and make sure that it's kind of slurry, and then you can actually feed it to the digester. But high solid anaerobic digestion it can literally handle anything, it can handle like you know yard waste, it can handle food waste, it can handle any kind of lignocellulosic biomass, okay, and if there are some little bit of contamination it doesn't actually affect that much. So the process is more resilient to you know like heterogeneity in the feedstock. So typical feedstock for wet type is municipal sludge and food waste, but food waste need to be treated. High solid anaerobic digestion you can use food waste, garden waste, any kind of high solid waste and including lignocellulosic biomass, okay. For wet type anaerobic digestion, after the digestion process is done, the digested it still contains lot of water, right. So you cannot actually directly use it as a fertilizer, you have to dewater, you have to do the solid liquid separation. But high solid whatever coming out, okay, it's mostly solid, right, with let's say 60 to 70% moisture content. Still you don't need to do any like dewatering process, you can maybe you know do further composting if pathogen content is high and directly apply to the land. So high solid anaerobic digestion one of the benefit is less water, less capacity required. So we need smaller reactor, less heating cost, and it can handle different types of feedstock, okay. So benefit is small footprint, lower heating cost, very resilient system. So if you have some impurities like sand, fiber, any large particle, you can still actually use them as a feedstock without any pre-treatment process. And you need less critical process equipment, like you know you don't have any mixing, right. So you don't need to run any pump or motors 24/7, okay. Less maintenance in the system, but still the system needs actually like special you know like feature for or special equipment for loading and unloading, okay. So typically it's a batch process, you have a bioreactor, you open the bioreactor, you load the feedstock, you leave it for certain residence time, and after the process is done you open the reactor. But before you open the reactor it's actually kind of very critical, because you still might have some gas, methane gas, which is flammable, right. There could be some toxic gas like hydrogen sulfide. So that's why before you open the digester, after the digestion process is done, you have to actually purge the digester with some nitrogen gas or you know like to make sure that you don't have any toxic gas, okay, inside. Then otherwise it's going to be hazardous for the operator. So that's why, and you need some special equipment because you are dealing with very heterogeneous feedstock. So you need some process equipment to load and unload the digester. So which still gonna be little bit expensive. And another challenge is the process produce biogas, okay, but it's a discontinuous process. It's like microbial growth curve. Initially biogas production gonna be low, okay, and then biogas production gonna increase. It's gonna be stable for some time, and then it's gonna decrease. So that means your daily gas production is not same, right? So if I wanna use it for heat or electricity or something, I need, because if I produce electricity, I cannot store electricity, right? So one day you might have some surplus, and one day you may not have enough electricity. So you have to deal with the discontinuous biogas production. So sometimes some facility, what they do, they have some like big biogas bag, okay, so they store the gas, and then they utilize them on a discontinuous basis, okay. And in many cases lower methane yield compared to wet type anaerobic digestion, and mass transfer limitation, it's a major challenge, okay, and you are dealing with very big particle size of feedstock. It's not homogeneous. So that means always gas production, okay, gonna be lower compared to wet type anaerobic digestion. But I still feel that comparing wet and high solid anaerobic digestion, it's like a comparing orange with apple, right? Because they are two different types of, and they can deal with two different types of feedstock. So we should not compare them side by side. And potential reason for low biogas production and instability in the process is recalcitrance of lignocellulosic biomass. Because lignocellulosic biomass or yard waste, you have something called lignin, right? So if there is high lignin content, it's kind of inhibitory to microbes. So that's why sometimes degradation efficiency is not that good. Slow methanogenesis kinetics, it's like a common problem for both wet type and high solid anaerobic digestion, because methanogen, they are slow growing microbes. Mass transfer limitation, because we don't have active mixing in the process. So mass transfer limitation is always there. One of the common approaches, we can have a leached tank, okay, where we can have liquid inoculum and we can recirculate, okay. That can help us to overcome the mass transfer limitation to some extent. Acidification of digester at high organic loading rate. So in high solid anaerobic digestion, we are dealing with solid organic waste, right? So it's much more concentrated. So that means they are going to be high organic loading rate in the process, and high organic loading rate, we know that acidification could be a problem. Ammonia inhibition, again, it's more concentrated, okay. So like wastewater sludge, how much ammonia you can have? Wastewater, its ammonia content is 50 milligram per liter, but in solid waste it might be few thousand milligram per liter, right? So and a high ammonia content can inhibit microbial activity. And again, nutrient imbalance could be problem. Sometimes we may ignore the significance of carbon to nitrogen ratio, right? So and it's hard to balance right? Because every day the wastewater, solid waste is coming from different places. They can have different characteristics, right? So and different carbon to nitrogen ratios. So which can also create some imbalance in the process. So any questions so far? Sorry, what? This one? This one? Okay. Sorry, what? Oh, sorry. This one, yeah.
So volatile fatty acids are produced. Thereafter osteogenesis, and the right side, hydrogen and carbon dioxide being produced. there any possibility of converting that network to form only hydrogen carbon dioxide by making use of any certain bacteria or something like that? That
Yes,
is so, hydrogen will be the good fuel.
that's actually a very good actually question. So yes, actually some processes are using that approach. Okay.
Maybe,
So this is called dark biohydrogen fermentation. Okay. So what we do in this kind of process, we kill the methanogen intentionally. There are some approach actually you can kill the methanogen. So you actually end the reaction here. So what you get in gas phase, you get hydrogen and carbon dioxide, and liquid phase you mainly get volatile fatty acid. Okay. And some plant actually so previously there were a lot of research on two-stage anaerobic digestion. So first stage you produce hydrogen and VFS, and second stage you take the liquid and you kind of VFA further actually treated with anaerobic digestion process. Yes, you can produce biohydrogen as well.
methane is a greenhouse gas and it's toxic to environment also.
Sorry,
Methane is a greenhouse gas.
but you are actually combusting, you are producing heat and electricity,
Upon combustion again it produces
producing carbon dioxide, which is kind of less dangerous.
we are losing some energy also.
Yeah, but even you are going to produce hydrogen plus carbon dioxide, so you have to deal with the hydrogen. Yes, when you actually combust hydrogen, it's going to be mainly water, right? So no carbon dioxide, but still that if you go with dark fermentation process for biohydrogen, you still going to have carbon dioxide that you have to deal with. Okay. But why biohydrogen actually dark biohydrogen production? Because we know that there is a lot of discussion about hydrogen economy these days, right? In many countries they want to actually build infrastructure on hydrogen, okay, as a cleaner fuel. But the major challenge with dark biohydrogen fermentation is the yield is very low. Okay, yield is very low, so we cannot get more than 2 mole per mole glucose or hexose. Okay, so which is, if you see chemical reaction from 1 mole of glucose, I think we can get up to 12 mole of hydrogen, but dark fermentation process you can get only 2 mole, right? So that means yield is very low, and process actually has lot of challenges still. So that's why it's still in research phase, not commercially actually implemented. So there are many commercial high solid anaerobic digestion process available in the market. Okay, so and majority of them they actually developed in Europe, and I think as I was mentioning, Europe they are much more advanced, okay, in this field, because they did not have any choice, right? Because they did not have enough space to build landfill, so they had to actually develop something that can actually help them to address their waste management challenges. So that's why there have been many commercial high solid anaerobic digestion processes, and majority have been developed in Europe. So and you are going to see they have some similarities. So for example, Drenco process, its residence time is 14 to 20 days, Compo gas 15 to 29, garage type 28 to 35, Biofarm 28 days, Biocell 21 days, CBAC 25 to 30. So more or less on average residence time for high solid anaerobic digestion process is close to 4 weeks to 1 month. Okay, so 25 days to 30 days. Okay, this is in most of the facilities they are actually kind of like mesophilic, I would say 35 and 55, 50 to 58, 50 to 55 to 60. This is it doesn't say anything, but it can be either mesophilic or thermophilic, but again I would say mesophilic is, I think majority of the AD facilities worldwide they go for mesophilic, because thermophilic they have more disturbance problem. So high solid anaerobic digestion, okay, the facility, some of the and most of there are some common feature of each commercial processes, okay, and some of the facility it's gonna look like garage or storage facility, okay. So you have a like box type reactor, okay, with some door, gas tight door. You basically open the door, okay, load the feedstock and then close it, okay, and leave it for about 28 to 30 days, and after the process is done you take them out, okay. So this is a common process, but again if you don't have any mixing, there are going to be significant mass transfer limitation in the process. So that's why most of the facilities or commercial design, they include a secondary tank. Sometimes we call it leachate tank or percolate tank, okay, where we have some liquid, okay. Sometimes leachate can be collected from here, or sometimes some facility they add liquid inoculum, okay. So liquid inoculum, and they kind of intermittently they recirculate that inoculum between two tanks. So that kind of provide some sort of like passive mixing in the process. So you can overcome mass transfer limitation in the process. So organic fraction of municipal solid waste is kind of this is sometimes called box type or garage type design. So I think like here you see garage type, okay, they call it garage type design. So you have a gas tight door and you collect the leachate and you recycle it back, and a kind of you can have a sprinkler at the roof of the tank, and then you can actually kind of distribute the leachate, and so that's going to actually provide some mixing, and you can collect biogas from the top. And there are at least two commercial design that is actually based on this concept. One is smart farm, one is biofarm, okay. I think both of them are either developed in Germany or Netherlands, I can't recall exactly, okay. So this is an interior of the tank, and you can see, I'm not sure whether you can see it properly, but there are some pipe installed at the roof of the tank, okay, and they are actually doing some wet commissioning using water, okay. And this is how it's going to look like after you load the digester, okay. But obviously this was in the beginning of start. You cannot, during anaerobic digestion process, you cannot open and take picture, right? It's during the loading process. And I put actually YouTube video link, okay. So most of the commercial those vendor, they have some nice videos on YouTube, okay. So you can go and actually check, okay. I provided the link for every design, but we are not going to actually watch video on in the class, but I think you can maybe tonight when you have the lecture note available, you can go and check online those videos. But in addition to box type design, there could be other design, okay. So one process called Drenko process, if I am correct, that process was actually developed in Japan, but I might be incorrect as well, so please check, search online, but I am pretty sure it was developed in Japan. So that is kind of semi-continuous process. So that's a silo type reactor, very tall reactor, okay, and you are pumping your feedstock from the bottom, but they are actually entering to the digester from the top. So there is actually pipe, you are injecting from the or pumping from the bottom, but actually it's entering to the reactor from top, and when it's kind of going down, the reaction, they have interaction with microbes and organics, and it's kind of degrading, and they have a large gas holder where they actually collect the biogas, and like feedstock is added in the system, but a part of digested is actually kind of added to the fresh feedstock. So because you have to make sure that you also providing inoculum, right. So most of those design in high solid system, after the batch is done, you actually recycle a portion of the digested is in inoculum, okay. Otherwise, like if you just start with feedstock, you have food, but you don't have enough microbes, right. So you need both microbes and feedstock. So that's why most of the time digested, a portion of digested is recycled back to the process. So it's a silo shaped reactor, and limited amount of fresh feedstock is added to the digested, okay. And technology operate, they claim that this process can handle up to 40% solid, okay, up to 40% solid. there is another design which is actually a plug flow type reactor. Okay, so you are basically you have a plug flow type long reactor. Okay, and then actually they have an internal mixer here, as you can see here. That mixer, it's kind of continuously rotating to provide mixing in the feedstock, and there is some head space in the pipe or inside the plug flow type reactor. So in head space biogas is accumulated and it's collected. So solid waste is entering the system from one end, and you have continuous mixing and reaction happening, and when it's actually leaving from the other end, you have digested. Okay, so this is another design, and this is called compo gas technology, and they claim that they can handle from 23 to up to 30% of solid, okay, in their process. So yeah, there are many commercial design. So now we understand now, okay, there are two types of anaerobic digestion process. Okay, one could be wet type, one could be high solid, but for high solid it's more appropriate for solid organic waste. Okay, and there are many design available, but most of the design you know, like you can have I would say the common design is you have a digester tank and you have a like separate leachate or percolate tank, because I think North America several facilities they are actually using this design nowadays. But you can have other design like Drenco process or compo gas process like plug flow or silo type reactor as well. But let's say you are working in a consulting company or you are working in a municipality. Okay, so to see the feasibility of the process, okay, let's say someone come to you, okay, and say, okay, you know what, I have that feedstock, okay, whether I can you suggest me, let's say you are an expert, someone come to you and ask you, okay, you know what, can you tell me whether, you know, like if I actually treat this waste in anaerobic digestion facility, how much biogas that I can generate, because biogas it's ultimately your you know, way of generating revenue from the process, right? So how we can do that? Any thought?
It's totally depends on the field ratio. Totally depends on the field that we have to use on the digestion.
Yeah, exactly.
Like quality rate can be maximum.
It depends, but sometimes the poultry waste may have high ammonia, right? But what you are going to do if someone come to you and ask you, okay, you know what, like how much methane I can generate? So there are different approach, okay, to estimate how much, what is the methane potential in a feedstock, okay. Yeah, what is the methane generation potential? Sometimes we call biochemical methane potential of a feedstock, okay. So this is a term that is actually widely used to see, like, you know, if we use a feedstock for anaerobic digestion process, how much methane we can get, okay. So sometimes we can actually do theoretical calculation, sometimes we can actually do some lab scale experiment, but theoretical calculation gonna give you maximum number, right, like theoretical number, but when you are gonna run like real process, maybe you can recover 50% or 40%, right. So there are some approaches that can actually we can use for theoretical calculation, and that's actually sometimes very useful, especially when you are in consulting and when you want to actually make some decision without building the, like, you know, we cannot just build the facility and see whether it works or not, right. So first we have to start with this. So if we consider food waste we have carbohydrate, protein and lipid, right. And carbohydrate, protein, lipid, each component they have different methane potential. So for example, if you see carbohydrate, per kilogram of carbohydrate as volatile solid. So anyone familiar with the term volatile solid?
Yes.
So what is volatile solid?
Solid, when you put it at high degree Celsius, it will be evaporated.
Yeah, so basically it's organic.
Yes, that is organic.
Basically it's all. So we learned about, you know, in day one we learned about the term called volatile suspended solid. right, VSS. So to do VSS, we filtered the sample, but this is called volatile suspended solid, but here we use the term for solid waste, we use the term called VS, volatile solid. Why? Because solid waste we cannot filter, right? So that's why we call it, instead of volatile suspended solid, we call it volatile solid. That an indication, okay, how much organic is there, okay, and the method is same. You can also do total solid. So instead of TSS, we use the term TS, and instead of VSS, we use the term VS. So what is total solid? The same method. You can get a certain amount of sample, put it in oven at 100 degrees Celsius and leave it for an hour, and then after you come back, your like moisture is gone, right? Yeah, exactly. So moisture is gone. So what you have is basically total solid, right? But now if you keep that sample at 550 degrees Celsius, okay, then you are gonna get rid of all the organics at 550 degrees Celsius. Then what's gonna be left? It's gonna be ash, right? Or fixed suspended solid or fixed solid. So at 105 degrees Celsius, after you take out, you are gonna have TS. At 550 degrees Celsius, what you are gonna have left, it's fixed solid. So from the difference TS minus FS, I can get VS, right? And VS is basically my organic. Okay. So in food waste, organic can be in the either carbohydrate, could be protein, could be lipid, okay, and different component have different methane potential. And as you can see here, for carbohydrate, your methane potential is 0.415 meter cube per kilogram of VS. For protein, it's 0.496 meter cube per kilogram of VS. Lipid, 1.014 meter cube per kilogram of VS. Okay. So if we know the carbohydrate, protein and lipid content in our feedstock, we can measure the what is theoretical potential. Okay. But definitely the theoretical value not gonna, like we cannot achieve theoretical value. For example, here you can see for which compound actually methane potential is high here, lipid, but lipid is very difficult to degrade. Yeah, even if you have high lipid content, it can, those long chain fatty acid can completely inhibit the methanogen. Okay, so but at least it can give us some indication, okay, how much methane can be generated theoretically. So let's see an example. Calculate maximum methane potential of food waste based on the following composition. So we have 88% volatile solid, 88% of solid is organic, carbohydrate is 47.3% of VS, protein 29.5% of VS, lipid is 15.5% of VS. So we can start with a basis. We have 1 kilogram of food waste. So that means in 1 kilogram we are going to have 0.88 kilogram of volatile solid, right? Our volatile solid is 88%. So 1 kilogram we are going to have 880 gram of volatile organics. So now I know the composition of carbohydrate, protein and lipid. I can multiply by those percentage and I can know in 1 gram how much carbohydrate, how much protein and how much lipid I have, right? So now I have that table, okay, where I have that yield, theoretical yield. So I can multiply by that theoretical yield and I can get from carbohydrate how much methane I am going to get, from protein how much methane I am going to get, and from lipid how much methane I am going to be getting. And so this is going to be, so 1 kilogram of food waste can give you up to 450 or 445 liter of methane, okay. But again we have to keep that in mind that it's a theoretical calculation. In practically maybe we are going to get 40 to 80, like 80% could be highest, okay. Sometimes like it could be, it depends on not just the characteristics of your feedstock, it's also depend on the operating condition of your digester, right? But that can give you some idea, okay? So if you know, if someone come to you with food waste, you can simply try to see, okay, what is the carbohydrate, protein and lipid content, okay, and you can do some rough estimation, and you can actually tell your client, okay, this is the theoretical, maybe we can recover 50%, okay, in the process. So you can even estimate biogas, there are some biogas market price, and you can see what would be the approximate revenue generation from the process, right? That can actually help you to decide whether a biogas project gonna be economically feasible or not. So another thing, so here we talked about food waste, but how about wastewater? Let's say we have black water. We want to see how much waste methane can be generated from black water. For wastewater, we use COD, right? Instead of like solid content or VS, we go with COD. So how much methane can be generated, okay, if we degrade 1 gram of COD in an anaerobic digestion process? So we can also do a theoretical. So let's say some company, industry come to you and say, okay, you know what, we have a very concentrated industrial wastewater that we generate, okay, and this is our COD, which is very high. We are thinking about some anaerobic treatment. Can you tell us, okay, how much methane we can generate? So you can simply ask them, okay, what is the COD of your sample, okay, and based on that you can come up with some theoretical calculation, and then you can say, okay, you know what, like if the process efficiency is 50% COD removal efficiency, then we might actually get that amount of methane from the process. So how we can actually calculate them? So COD, what is COD? Chemical oxygen demand, like how much oxygen that you need to oxidize some organic compound to carbon dioxide and water, right? So here, so methane, if I completely oxidize to carbon dioxide and water, I need for 1 mole of methane, I need 2 mole of oxygen, right? So 64 gram of oxygen is needed for 1 mole of methane, right? So 2 multiplied by 32, 64 gram of oxygen, or oxygen is our COD, right? So 64 gram of oxygen is needed for 1 mole of methane. So that means 64 gram of COD gonna give you 1 mole of methane. And in our high school, we learned that actually at STP, 1 mole of gas gonna occupy 22.4 liter, right? At STP, yeah. So 22.4 liter. So 1 mole gas gonna be 22.4 liter. So now I can write 64 gram of COD gonna give me 22.4 liter of methane at STP. So 22.4 liter, so divide by 60. So per gram of COD gonna give me 0.35 liter of methane at STP. But maybe you can ask your client, okay, whether you are thinking about mesophilic digestion or thermophilic digestion, right? So this number we are getting is for STP, but at high temperature volume gonna be little bit higher, right? So we can do the correction for temperature. If I am running it for 35 degrees Celsius, I can do the correction for temperature. So at STP it's gonna be 0.35 liter, but at 35 degrees Celsius it's gonna be 0.395 liter, little bit higher, right? So and then we can tell, okay, you know what, like with typically 50% efficiency, we can get what, about 200 liter per kilogram of or 0.2 liter per gram of COD, okay? So that's actually another approach that we can use. But for solid waste, it's hard to measure COD, right? Because it's like very heterogeneous mix. So COD measurement is very challenging. So for solid waste, what we can do, okay, we can calculate methane yield from elemental analysis or ultimate analysis, okay. So how we can do that? So if we do the elemental analysis for a feedstock, okay, there is an actually device called CHNSO analyzer, okay, that can actually you can actually prepare your solid waste feedstock as a powder, okay, possibly as a powder, and that actually machine can measure the carbon, hydrogen, oxygen, nitrogen and sulfur and ash content, okay, in your sample. And if you know the elemental composition of your sample, you can actually develop a chemical formula for that waste, okay. And then when you know the chemical formula, we can use this reaction stoichiometry, okay, to calculate what would be the methane potential. So organic compound, they are composed of carbon, hydrogen, oxygen, nitrogen, sulfur, okay, and during anaerobic digestion process they are going to be converted to methane, carbon dioxide, ammonia, hydrogen sulfide. So if we can establish a chemical formula for our solid waste, I can calculate how much methane I can get theoretically, right? So how, now the question is how to establish chemical formula. So we can do elemental analysis using CHNSO elemental analyzer, okay, and then we can establish a chemical formula. And typical elemental analysis or ultimate analysis, this is actually the composition for food waste and yard waste typically. But obviously if you have a sample and if you are working with your client, you have to get the sample, you have to do the elemental analysis for your sample, okay. This is kind of typical. For food waste, for example, you have 48% carbon, 6.4% hydrogen, 37.6% oxygen, 2.6% nitrogen, 0.4% sulfur and ash 5%. So inert material is 5%. Yard waste, it's like more or less the same, okay. So we are gonna do an example, okay. We are gonna use this elemental analysis, okay, data, and we are gonna try to establish a chemical formula for a feedstock, okay, and we are gonna try to estimate what would be the methane potential for a sample. So let's see an example. A pilot scale high solid anaerobic digestion facility has an annual processing capacity of 100 tons of feedstock, okay, on dry basis. Facility primarily process 70% food waste and 30% yard waste. So whatever coming to the facility, they have 70% food waste and 30% yard waste, okay. And assume that 60% of the feedstock actually undergoes biodegradation and can be converted to biogas, right? And the process operates under mesophilic temperature at 35 degrees Celsius. We want to calculate the annual methane production. So annually, so how much methane we can get from the process, and this is the ultimate analysis data that I got from previous here, okay. So I am going to use the data and I am going to consider in my feedstock I have 70% food waste and 30% yard waste. If I mix them together, what would be the chemical formula, and then I will go to this reaction and I will try to calculate what would be my theoretical, and that's actually very handy tool. It's like really widely used, not necessarily just for research, even in industry we actually use that approach. So first thing, I have this table and I can start with a basis. Let's say I have 100 gram of waste, okay. If I have 100 gram of waste, I am going to have 70 gram of food waste and 30 gram of yard waste, right. So 70% is food waste, 30% is yard waste. So now I know that out of that 70%, 48% is my carbon, right. So I multiply by 0.48, and so that means in my 70 gram food waste I have 3.6 gram of carbon. Now, oh sorry, not 3.6, 33.6, okay. So number actually, so 33.6 gram of carbon. hydrogen I have 6.4%. So 70 multiplied by 0.064. So 4.48 gram I have hydrogen. Okay. So I can do the same for each component, right? I can do this. So for example, if I want to do sulfur, it's 0.4. So I'm going to have 70 multiplied by 0.4 divided by 100. So 70 multiplied by 0.004. So I have 0.28 gram of sulfur. But so we can, it's like simple math, right? I can use the ultimate analysis data and I can calculate how much carbon I have, how much oxygen I have, how much hydrogen I have, how much nitrogen I have, how much sulfur I have. But why I excluded ash?
Because thermoenergy when
Doesn't participate in the reaction.
Huh?
Doesn't participate in the reaction.
Yeah, it's inorganic, right? So it doesn't matter whether we include or because ash is, it's not going to contribute, right? We are actually trying to establish a chemical formula for the organic part. So that's why ash is always excluded from the process. So now you can see in total, if I have 100 gram of feedstock, I have 47.94 gram of carbon, 6.28 gram of hydrogen, 37.70 gram of oxygen, 2.84 gram of nitrogen and 0.37 gram of sulfur. So let's summarize them in another table. So I have, this is what I have, right, from the ultimate analysis. Now this is in gram. So now if I divide those number gram by molecular weight, which is gram per mole, okay, what I am going to get? Number of mole I have. So for carbon it's 12, hydrogen is 1, it's hydrogen 1.007, but you know, like when we calculate we try to like round the numbers, so I am just using 1. Oxygen 16, nitrogen 14, sulfur 32. So if I divide them by the molecular weight, I can get number of mole, right? So 3.995 carbon, hydrogen 6.28, oxygen 2.3575, sulfur you can see very low. You can still write a chemical formula from that, but it's, we don't like lot of fraction, right? So what we can do, we can normalize. We can divide all number by the smallest number, which is the mole of sulfur. So if I divide all number by the smallest number, so sulfur gonna be 1, and then I can get carbon gonna be 346, hydrogen 543, oxygen 204, nitrogen 18. So I can get a chemical formula which is carbon 346, hydrogen 543, oxygen 204, nitrogen 18 and sulfur. So this is my chemical formula that I get from elemental analysis. Okay. So now I am actually ready to use this equation, okay, or chemical reaction, right? So this is my organic compound. So I have value for A, B, C, D, E. E is 0 because sulfur just 1. Sorry? Oh, okay, E should be 1. Yeah, because sometimes we exclude the sulfur. Okay, yeah, I can correct that. But anyway, so 1 mole of this compound, okay, 1 mole of this compound gonna give me this amount of, it's gonna be actually 1, not 1 actually, it's gonna be 1 divided by 4, so minus 0.25, right? So again, it's not gonna change the final number that significantly, but 1 mole of this organic compound gonna give me that amount, that mole of methane, right? So I can calculate the molecular weight of this compound, which is 8243 gram of this compound per mole, right? So I know I have 346, I can multiply by 12, 543 multiply by 1, oxygen 204 multiply by 16, nitrogen 18 multiply by 14, right? So this is going to be my molecular weight, and I am going to get 183.125 mole of methane. Now the facility is treating 100 ton of waste and 60% can be degraded in the process. So 100 ton, when we actually convert to gram, it's 10 to the power 8 gram, right? And 60% can be degraded in the process. So multiply by 0.6. So this amount of this organic compound gonna give me that mole of methane, right? So now that mole of methane. So now again we know that for 1 mole at STP it's going to be 22.4 liter. So I can multiply by 22.4. So this is going to be the amount that I have at STP, and then but I'm going to be running the facility at mesophilic temperature at 35 degrees Celsius, right? So now we have to do the temperature correction, and then this is going to be my final number that I am going to get. Okay. So if we can do the elemental analysis for a solid waste, we can establish a chemical formula, and we can use that chemical formula to calculate theoretical methane potential for a sample. But again, this is a theoretical number, right? But in reality, maybe you are gonna, this is not theoretical because you already considered that 60% gonna be degraded, right? So it's not maximum methane potential. So any questions so far? I'll correct that part, and I'll so before I share the thing, like I can actually like correct that number there. Actually there is another chemical another reaction that is excluding sulfur, because sometimes sulfur content, if it's really low, you can actually ignore the sulfur part. Okay. Any questions so far? We're good? Okay, so now we learned 3 theoretical approach. Okay, so first one is, if we know the protein, lipid and carbohydrate content, we can estimate what is the methane potential. If we are dealing with wastewater, if we know the COD of the sample, we can estimate. Huh?
COD or DOD?
COD, because this so this is actually COD, but again, like BOD means it's biodegradable. So if you use BOD, that is kind of like gonna give you what you can get practically. But COD is more handy too. Actually, it's easy to analyze. Within 2 hours you can get some number, right? And again, you can decide, okay, or you can just make some assumption, 50% gonna be BOD, okay, or if you know the COD to BOD ratio. So again, you can do because as long as we know the relationship between our COD and BOD, they can be actually used interchangeably, right? So far we learned 3 approach. From protein, lipid, carbohydrate content, which can be handy for food waste. We learned for wastewater, if we know the COD, we can do some calculation. For solid waste, if we know the elemental analysis, okay, carbon, hydrogen, oxygen, nitrogen and sulfur content, we can estimate methane content by establishing a chemical formula. But how we can do that experimentally in the lab? Sometimes you may want to further validate it using kind of some sort of lab experiment, right? Especially when you are doing some research. So we can do that using a technique called biochemical methane potential test, or BMP test. Yeah, BMP test. So how we can evaluate the methane potential of any waste or wastewater, high strength wastewater, experimentally. So we can use a test called biochemical methane potential test. It's a very handy test, simple batch test, not very expensive, and required 1 to 2 months, mostly 1 month. Okay. So, and this is a typical setup. Okay, but there are some advanced actually device available in market, like commercial device. So when you do this kind of bioassay test, every day you have to go to the lab, you have to take biogas sample, do GC analysis to see methane content. Okay, you have to measure the volume of biogas produced. Okay, but there are some device in market right now. They can directly actually measure the methane volume. Okay, and the data can be recorded using software in the computer. So after you start the experiment, you don't need to even go to the lab. After the process is done, you can just get the data from the computer. But yeah, like last I think 10 years, this kind of equipment became very popular. But I remember when back in 2008 or 9, when I was running this kind of experiment, sometimes I had to stay overnight in the lab, because let's say I'm running 60 bottle. So for 60 times I have to take sample, go to the GC and do the analysis. But nowadays it's very convenient that, you know, like computer can record the data. And it's not rocket science. What happened, like, you know, biogas, you have carbon dioxide and methane, right? And you can have some sulfide. So if you pass that gas to some alkaline solution, okay, it can actually absorb all the acidic gases. So in the gas meter, whatever gas is going, actually it's mostly methane, right? So yeah, so this is kind of like a, but still they are charging, like this setup, this is actually from my lab. Okay, so this setup, I think we buy them about $10,000, okay, each setup for 6 bottle, or you know, sometimes we can run more. But this setup, I think it's right now market price is around $35,000 to $40,000. Okay, and it's not a rocket science, but still it's quite expensive device. Okay, but it's very popular to industry, because industry, you know, like when they run experiment, they don't want to actually spend a lot of time actually working in the lab, or, you know, like it's kind of very handy tool for them. So yeah, so now biochemical methane potential test, if you have a feedstock like either waste or wastewater sample, so first we have to characterize the feedstock. Okay, and for this kind of thing we typically go with COD measurement. Okay, and then we have to bring some seed or inoculum. So seed or inoculum, we can, if we have a, let's say, large scale AD facility in your city, you can go to them and you can ask them to give you some digestate, because digestate that is coming from full scale digester, they are already enriched with different types of anaerobic microorganisms, right? So you can get those kind of culture and use them as a seed or inoculum for BMP test. And for inoculum, we typically do VSS or VS. Okay, so sometimes if it's kind of slurry, you can go with VSS. If it's like solid, you can go with VS. So there is no strict rule for that. And then we have to design some bioassay, okay, or design some BMP test based on food to microorganism ratio. So what is food to microorganism ratio? We learned that yesterday. It's a balance between substrate and microbes, right? So that means, and we know that actually high food to microorganism ratio, it's not good. So that means you are actually giving more food than they actually can consume, right? So that's why there is a recommended range for food to microorganism ratio, and you should not go beyond that. And then after you start your experiment, you have to collect the methane production data and you have to do the data analysis. So typically BMP test, its food to microorganism ratio, it's range from 0.25 to 5 gram COD per gram VS. So COD is for substrate or waste and VS is for inoculum or seed. So based on food to microorganism ratio, so most of the time, like if you don't know what would be the optimum food to microorganism ratio for your feedstock, like it's better to go with low FM ratio. So most of the time, if we don't know, like, you know, what would be the optimum, we go with 1. Sometimes we try multiple food to microorganism ratio, but if we don't want to do a lot of experiment, we end up with doing, if I need to pick one food to microorganism ratio, I will go with 1. Okay. So, FM ratio here you can see it's like almost similar equation that we learned yesterday. So, FM ratio is gram of COD of substrate and M is gram of VSS or BS, whatever you use, of inoculum. And so, basically it is volume multiplied by concentration, right. So, if a mass of food divide by mass of microorganisms.
So here VSS of inoculum is just like ml VSS, just like VSS of inoculum.
Yeah, microorganisms, yes.
So it is just like ml VSS of this.
It's you can say MLVSS. I won't say, yeah, like it's MLVSS term is more used for activated sludge process, but here I would say VSS, okay, or sometimes you can do VS. Sometimes actually, like like digested solid content could be high and filtering may take really long time. So sometimes actually researchers they prefer VS instead of VSS. So now if you have a reactor or bioassay, okay, bioreactor, you are going to know what would be the working volume that you are going to be dealing with, right. So typically those bioreactor they are from 300 ml to 1 liter, okay. So we need to know if we have a certain working volume. So this is going to be, let's say if I need to know how much substrate I am going to add and how much inoculum I have to add to achieve certain food to microorganism ratio. I think someone has some question. So did you have a question? You had a question? Okay. Yeah. So now you can see I have two equation. So first I have to decide what food to microorganism ratio I am going to use. I have to measure that COD of my sample. I have to measure VS or VSS of my inoculum, and I am going to know what would be the working volume of my bioreactor. So if I know them, I have two equation and I can see I have two variable, unknown variable V1 and V2. I can actually estimate them V1, V2. So after I decide, okay, or estimate what is the volume of food waste or sample that I need and what is the volume of inoculum or and seed that I need, I can actually start my experiment, right. So first we are going to add volume of estimated seed and substrate in my BMP bottle, and then check the pH. So we have to make sure that when we start there is enough alkalinity in the reactor, okay. If there is not enough alkalinity, we have to add buffer and we have to actually adjust the pH to close to 7 or neutral pH. And then the step is we have to purge the reactor with nitrogen because it's an anaerobic process. So we have to make sure that there is no dissolved oxygen in there. And then after purging with nitrogen, we can close the reactor and we can put it in the incubator, and over time we can measure the gas volume and methane composition. But at the same time, okay, we have to run a blank test. So what is blank test? So blank test, we are going to have similar, like reactor, but for one reactor, the feedstock or substrate going to be replaced with DI water. And why is that? Because when you have like an incubation, like during incubation, you expect that gas is going to be produced from your substrate, but there are some organics in your seed or inoculum itself, right? So how do you know that there is no gas production from inoculum itself, right?
So it is just to subtract.
Yeah, so that's why.
So when we are going for absorption spectroscopy, then we do blank test.
Absorption spectroscopy for what? So here we want to know, okay, what would be the biogas production from seed or inoculum itself. So that's why we run a same test, but without any substrate, and we replace the substrate volume with DI water where there is no organic. So we call it blank. So if I have a test reactor, okay, test reactor I have, let's say 100 ml biogas production, and blank is showing me 10 ml. So I can assume that, okay, 10 ml, I am seeing 100 ml, but 10 ml is actually coming from inoculum, but I am interested about substrate. I am not interested about how much gas is actually coming from inoculum itself, right? So that means my true gas production gonna be 100 minus 10, 90 ml. So for that correction, we have to run some blank test, okay, and then you are gonna collect your data, and this is an example data, okay. So let's say, you know, from you are running the test for 17 days, and this is your daily gas production. So what we do, we kind of look into cumulative gas production data, okay. So cumulative gas production data, and you can see after a certain period of time it reached about 1300 on day 13, and then it kind of reached a plateau. There is not significant gas production after day 13. So if you see the graph, time versus cumulative methane production, you can see after day 13 it reached a plateau, right? So at this stage we can decide, okay, you know what, it's the experiment is done and we can stop the, you know, our test, okay. So when we should stop? When the cumulative gas production, daily gas production is kind of per day gas production is less than 1% of the total cumulative gas production, we can assume that it's kind of ready to stop. So for example, you can see here 1300, after that actually it was kind of quite stable, the gas production, right? So sorry, yeah. So now we can actually stop so that means there is not much biodegradable organics left in the process, so we can stop the experiment and we can start our data analysis. So now we are going to see an example with some calculation how the data analysis part is done, okay. So design a BMP test using food to microorganism ratio of 2 if the substrate and seed characteristics are given in this table. You can see you have TCOD, you have VSS, and working volume of the bioreactor is 500 ml. So my V1 plus V2 gonna be 500 ml, right? Conduct a COD balance if the final TCOD concentration is 15 gram. The experiment was conducted at 35 degrees Celsius. Total methane production was 1822 mil, and total methane production from blank was 100 mil. So my actual gas production was 1722, right? And this is my characteristics. So first I have to calculate what should be the volume for V1 and V2, right? So and food to microorganism ratio, in the question we mentioned that it's going to be 2, and I know the COD, I know the VSS, right? So I can actually plug those numbers. So 2, 40 gram per liter, 10 gram per liter, and my V1 and V2. So that means V2 equal to 2 multiplied by V1, and my V1 plus V2 gonna be 500 ml. So that means if I solve that, I need substrate, I need about 167 ml, and seed or inoculum I need 333 ml. Okay. So now COD balance. So what is COD balance? COD balance is done to make sure that the data that you are getting, whether it's reliable or not. It's kind of like, you know, some sort of like, you know, quality management in your test. So for any BMP test we do, we should also do a COD balance to make sure that we don't have any experimental error, and the data that we are getting we can trust. And why? Because it's an anaerobic reactor. What if you have some leak in the reactor and some gas actually it's kind of, you know, leaked from the reactor and you could not actually collect them, right? That could happen because it's an anaerobic reactor. It's a kind of very sophisticated. So that's why COD balance, it's a common approach that is actually done to make sure that the data you are getting it's reliable or not. So what is COD balance? COD balance is methane production that we are actually observing experimentally divided by methane that can be actually theoretically produced from the COD removal, because we know the initial COD that we put in the reactor, we know the final COD. Okay, so from the COD removal, because we know that per gram of COD, if we run, like from one of our previous slide, if we run our experiment at 35 degrees Celsius, per gram of COD should give me how much? Like 395 ml of methane. Okay, so now, so actual methane production was 1722, so 100 was for blank, and initial COD we know the COD for both substrate and inoculum, and we know the V1 and V2, right? So volume multiplied by concentration, we can get the mass of COD that we had in the reactor in the beginning, which was 12.34 gram of COD, and we know the final COD concentration, which was 15 gram per liter, and we know the total working volume, which was 500 ml. So that means final COD was 7.5 gram COD. So that means during this process incubation period, we removed 4.84 gram of COD. Okay, so we expect that, okay, that 4.84 gram of COD actually converted to methane, right? So we want to see whether it's kind of match with our experimental observation or not. So 4.84 gram of COD removed, and theoretical methane yield at 35 degrees Celsius from one of the previous slide, it's 395 ml methane per gram of COD. So my theoretical methane production should be 4.84 multiplied by 395. So I should see 1911 mil of methane, but experimentally I found 1722 mil of methane. So if I do use this equation, my COD balance is about 90%. So can we trust this experiment or not?
We can.
Huh?
Just we have to know that this is the correction factor.
Can we trust?
Yeah, I feel we can trust.
It's 90% close, not 100%. We can still actually trust that data. Okay, if it's like 80 to 90%, it's still acceptable, because you remember a portion of COD should go for new cell synthesis by microbes, right? So, and for anaerobic microbes, the 5 to 10% can go for new cell synthesis. So 90% is actually good enough. So if it's 90%, it's good enough. But some paper, if they actually report you, okay, they have like perfect 100%, don't trust that data. Okay, so you cannot get, yes, sometimes it could be coincidence, sometimes you could see close to 100%, but if it's 80%, still it could be reliable. Sometimes it could be 110%, so that means 10% could be some sort of measurement error, so which is still acceptable. Okay, any questions so far? Okay, so if not, then here we stop. So here we finish our second topic on anaerobic digestion, and all actually lectures note is going to be available to you, I think tonight, and tomorrow we are going to cover so this Gyan course on conventional and emerging processes, bioprocesses for waste and wastewater treatment. So far day 1, day 2, day 3, we mostly talked about like conventional processes, activated sludge process, composting process, anaerobic digestion process. So tomorrow my lecture is mainly going to be focusing on some emerging processes in this area. Okay, so thank you so much and see you tomorrow. Okay, thank you. right?
Not
At 4 p.m. Yeah. So meanwhile, you can have your lunch and you can actually interact with other faculty members. Yeah.